First of all, thank you, Rishi. It's a real pleasure to give this talk. And actually, I really wish I could go to India this time, and probably would have loved to give this talk in person. But it's something you're all suffering from. But I hope things are going to be back to normal very soon. Okay, so as you mentioned, like as Rishi mentioned, so the topic of my talk is blind analysis of isobar data for the CME search by the STAR collaboration. And so let me just, oops, I still have the issue with changing the slide. Okay. So let me just start by saying that what I'm going to talk about is this isobar program. It's been actually a long journey. It started in early 2018, and the actual paper was submitted on September 1st. Actually, I tried to submit it on 31st August, but I did a mistake, and just appeared. So you could see that it took like more than 3 years to complete this whole thing. So it wouldn't be possible, I have to say, with this unique detector that we have at RHIC, which is the STAR. And it's unique because of, in many ways, one of the reasons is its very large acceptance, several capabilities that actually made this measurement possible. Also, it wouldn't be possible without the versatile machine like RHIC. So in one word, I mean, RHIC doesn't need introduction. I think all of you are familiar, but if you have to put it in a sentence or something, there are many colliders in the world and will be built, but RHIC is one where the main motivation was to study. You can think of QCD Lagrangian, where you would like to think of the chiral symmetries restored. So in a loose way, I'm going to use some terms in a very loose way, colloquial way, so think of as if we could study this when the mass term is 0, nearly massless quark. So if you have a system where you have nearly massless quark, interesting things can happen, and the topic of my talk is actually something related to that. So just to put together, this versatility of RHIC and the unique capability of STAR are crucial to the success of our program. But remember one thing, a bit of digression in place here. RHIC is counting its days, and in a decade or so, this is going to be replaced by the electron ion collider, which could be another talk, and I would love to talk about that as well. So here I just show you, because it's an experimental talk, and I just to give you a quick introduction. What I show you is a goal-goal collision at the STAR detector. So this is a goal-goal event that was taken, at this time, 2016 at this time. So what you see is the central barrel of the STAR detector. It sits inside a magnet, and the central detector is called the time projection chamber. It covers the mid rapidity, can measure momentum, charge state, identify particles. So what you see in these blue and green lines are different charge tracks coming out of it. Because it sits inside a magnet, from the bending from the curvature we know the momentum. And the color is a representation of something that is related to identification. I don't want to go to the details. So goal-goal collided, it looks like more like a central collision, and lots of particles are produced, detected by the central time projection chamber. This detector is going to come to my talk again and again. But then you have a bunch of series of detector in forward, which are used to trigger the events. Okay, for example, the most important one is this event plane detector, which is over here. It covers a pseudo rapidity of like 2.5 to 5 or something like that. It sits over here. Okay, so that's just the introduction to the detector. So let me just quickly go through go to the next slide. I'm having a little bit difficulty in changing the slides. So the chiral magnetic effect. If you want to know about it, a couple of things you need to know. First of all, the pioneering paper, which discusses about parity violation in hot QCD, it was from DIMA, It appeared in 2005, as you can see. And then there are a series of papers followed. There's another thing you need to know. To the best of my knowledge, it was Larry who first called this phenomena as the chiral magnetic effect. I may be wrong, but that's what I think I know. But then the first method paper, the experimental paper on how actually you can detect it in heavy ion collisions, was discussed by, was introduced by Sergei Volosin in this very primary paper. And then after it took a while, like few years, for Star Collaboration to publish the first experimental paper. That is what I'm going to discuss this. So all of these things are great, and the question is, I want to say that where do we fit in? How I got interested it was actually a conference, or not a conference, it was a young researcher symposium, was organized by Larry and a couple of other people, Ru+Ru, and I think Professor Gavai was also there. And they gathered a lot of young people and to discuss new ideas. It was in 2014. So a lot of us were introduced to these topics, and we got interested. And I was told that, that although these things are out there, but remember that the person who originates a new idea is really not in the best position to follow it up, because the person is so scared that something will turn up which will knock the whole idea on the head. And so this also it took a little bit of time for me to realize what this actually means. It also means that if you have an idea like this, what you have to really do is put it to a test, and in a very unbiased way, as much critical and skeptic way as possible. And that's basically the theme of my talk, which is what I'm going to talk today, blind analysis. So let me just tell you why chiral magnetic effect is unique before I tell you how exactly it happens, just to give you some interesting aspect of it. So it is not a phenomenon that happens in your everyday life through motion of charge and in electromagnetic field. Imagine a situation like this. In an everyday motion of charge in electromagnetic field, what happens is charged particle in a magnetic field, it will go perpendicular to the direction of magnetic field. It's just basically like Lorentz force. Chiral magnetic effect is a phenomenon, no matter what is the inner working, which I'll get to. In this phenomenon, what happens is a current is generated parallel to the magnetic field. So you notice the difference here. The charges will move along the direction of magnetic field, and basically this is the equation here, where the current is generated to parallel to magnetic field, and the conductivity is chiral magnetic conductivity. And basically this is a generation of current along B, which is due to the constituents. There is a chirality imbalance in the constituents, and the early reference of this goes back here. But you see notice something odd and interesting here in this equation, right? Which is what I'm going to tell you. Think of this, okay? So hear me, and the context of parity. Think of Ohm's law, which is basically tells you, current, vector current along the electric field. So this is the relation. So you have a current, you have electric field, and then you have the usual Ohm conductivity. So you have a quantity that is parity odd here, so this is parity even. Okay, nothing funny here going on. This is normal conductivity. But think of chiral magnetic effect. So you have a parity odd quantity here, you have a parity even here. So this object, okay, which is the chiral magnetic effect, is related to parity violation. It's a parity odd. So that's very interesting by itself. Think of another thing, another unique thing. Again, think of Ohm's law. Think of the time reversal. So this is a T odd electric field, this is a T even. So this ohmic conductivity dissipative. Now look at the chiral magnetic effect. So this is T odd, this is T odd. So this is not non-dissipative. So that's very interesting by itself. And I'm going very fast. So as soon as this was introduced, first in relativistic heavy ion collisions, many connections were realized. The parity violation correction was immediately realized to have connections with the early universe and baryogenesis. This connection is weak, but you can look at this paper. I'm not the person to tell you. Also, the condensed matter in Dirac semi-metals, which is also materials like zirconium pentatelluride, similar effect was observed in condensed matter experiment. You could look at that paper here. The T-odd feature of CME was also realized to have connections with phenomena like superconductivity. And this is kind of a recent paper where it was realized that in quantum computers, you can replace the qubits with the chiral qubits, and in future quantum computers, you could build based on these phenomena. Not only that, if you think of future high energy experiments like electron ion collider, there is also a connection. The Weizsäcker-Williams transverse momentum distributions inside these colliding objects are actually related to the signal, that we will measure. The thing that generates the signal in CME, they are related to these intrinsic gluon distributions that are related to helicity and the unpolarized one. So we study a lot of phenomena in heavy ion collisions, but this seems to have incredible scope and connections, which gets us excited. So coming to our case, CME in hot QCD medium, that's the thing we want to discuss. So I just wrote down what are the key players in the game. There are 3 key players in the game. So first one is actually this, what you have to have is a deconfined medium of massless quark, which means the chiral symmetry is restored. So you have 4 such objects. You have a right-handed quarks where momentum and spin are aligned. This is right-handed object. You have the same for anti-quark, and then you have the left-handed quark where momentum and spin are anti-parallel, misaligned. Let's say that way. And then you have the same for the anti-quark. Now note that the yellow and green represent quark and anti-quark. This symmetry you cannot violate. You are not allowed to violate in QCD. But the symmetry between the left, the number of left and the right, that you also classically is obeyed, but this is what was argued that due to anomaly, you break it locally, at least in the QCD medium. And what are the exact mechanism? I don't think I could talk about that, but someone like Sayantan or Sorendu is a very good person who could talk about that. That there are mechanisms that can create imbalance in our heavy ion collisions. When the heavy ions collide, we know that at least it's sufficiently high energies. The initial state can be described by a classical gluon field, which has where the chromoelectric and chromomagnetic field are parallel, and this is generates certain topology where locally at least you could generate imbalance between right and left-handed quarks, and you could look at these papers if you are interested. So that's the second element. Then there is a third element. Even if you have 1 or 2, it's not sufficient enough. What you generate is a imbalance of chirality. These top 2 conditions are to generate what is called generate chirality or chirality genesis. In order to observe, we don't know how to measure chiral the imbalance in that way, but in order to really observe in experiment with whatever we can measure, you need this presence of a strong magnetic field, electromagnetic field, okay? And we know that ions are carrying protons moving very fast, and they are like 2 parallel wires carrying current in opposite directions. So you generate enormous magnetic field, which is of the order of ion mass square. And you could ask that, what are the evidences of it? We do not have a direct evidence of how much magnetic field we create in really these heavy ions. Griffith would, or not, if Jackson or something would give you that the magnitude is m pi ion mass square or something. But in ultra-peripheral collisions where the nuclei misses each other, we know that just the electromagnetic field interact and produce pairs of electrons or something. We at least know electromagnetic field is strong enough, more than experimentally we know it's more than electron mass square but theoretically you should have of the order of ion mass square, the scale. So once you have these three, you will then have the chiral magnetic effect. So let me quickly tell you using 4 steps what this is. So first you produce massless quarks in the system, up, down, sorry, not up, down, but quarks, anti-quarks, left-handed, right-handed, but their spins are all aligned, but they are chiral, okay? So if something is right-handed, at least over certain time scales where the symmetry is there, they remain right-handed. So left-handed remains left-handed. So this imbalance you cannot destroy. It doesn't dissipate away at least till they are chiral. So, but they are randomly oriented. Their spin are randomly oriented. As soon as the magnetic field, because the magnetic field is there, they align the spin. But remember, the quarks get aligned along the B field, and then the anti-quarks will get aligned anti-parallel to the magnetic field. So it's just because of the magnetic moment. But nothing funny still happened, okay? The funny thing starts to happen when you create the imbalance between left-handed and right-handed quarks. So I want to demonstrate it by, let me try to make it disappear. I tried to remove the left-handed here. If you only have right-handed, you will generate a net current along magnetic field, and it will be roughly like related to, it's basically this equation. There's nothing special here. Magnetic current along, vector current along magnetic field. So excess right-handed creates electric current along the field. The opposite would happen when you have more left-handed. Take a look at these diagrams later. So basically, if you have more left-handed, you generate a current anti-parallel to a magnetic field, and you don't know, right? In an event, in some region, you could have either way. So we have to consider this parity odd feature of this specific phenomenon if you want to detect it. So that's what we need to remind, and let me quickly tell you how to experimentally observe this. Before I tell you how to experimentally observe CME, I need to first tell you something which is called the flow, anisotropic flow. It's a very widely studied phenomenon, and it is related to determination of B field direction. But let me just tell you this, that what I show you here is an image of an event. You still see the part of the star detector, time projection chamber, but you see a projection of it. You see the tracks coming out. We know, actually, it's a very well studied phenomenon called anisotropic flow. In an event, you will find a direction where you are likely to see there is a more probability of particles to be emitted, and the probability is roughly like 8% more compared to the exact perpendicular direction. You will have like equal amount of less particle. So this resembles an ellipse, right? So you have like a major axis and minor axis. So this is called elliptic anisotropy. And there are several reasons it happens. It's hydrodynamic flow or initial state. But note that in the next event, this direction will change, right? It will always be random, because depending on how the nucleus collides. So if you want to really measure this anisotropy, it immediately becomes clear to you we at least need 2 particles, right? So you need the first particle, 1 particle, and you need another particle. So one would represent the reference plane, and the other one will measure the anisotropy. So this is the coefficient V2 that is represented as like 2 times phi 1 minus 2 times psi 2. So this is the plane of direction of the anisotropy, and this is the angle, and then this whole object is the moment, okay, that measures the strength of an anisotropy. Or you could do it in a different way. Instead of taking a plane like this, you could just take 2 particles, and it doesn't matter, you need 2 particles to measure this. Pair-wise correlation has to be measured. Why is it important? Why am I telling you this? Because we know that this anisotropy was created by overlapping nucleus, and the direction of this anisotropy is roughly correlated with the direction of the magnetic field. Just because of the collision geometry, this happens. And so basically, if we just measure the anisotropy direction, now we will be able to know where we'll be able to have a handle of the direction of magnetic field. That's the first step you need to know to study CME. Once you have that, what is the next step? Obviously, you now want to see if in an event positive particles are going along the magnetic field and the negative particles are going opposite to the magnetic field, right? So how are you going to do? You could do the same thing like we did before, right? You take again the direction and try to measure one of the particle and make sure if it is positive or negative. But remember, you will have a problem. If you just take two particles or like one plane and another particle, you will run into a problem because it always flips like the magnetic field direction. It's a parity odd effect. So the positive will go up and negative will go down. In the next event, it will again flip because we don't know whether there are more right-handed or left-handed. So this parity odd feature you cannot measure using a pair of particles. You need to measure the correlation of triplets. Statistically, you need to measure triplets. So in other words, you need to get the plane. You need to look at a positive particle, and at the same time you need to make sure a negative particle is going opposite. And if you pick up two positive particles, you need to see if they are going in the same direction. If you don't do that, it's very obvious. I mean, I could come back to this discussion. You lose this, you lose this parity odd feature, and everything will become zero. So this is the observable now. Look. For anisotropy, it was 2 times phi 1, 2 phi minus 2 psi 2. But here I have two particles, angle of two particles relative to the plane, okay, and the cosine of that. This is called gamma correlator, and this is the observable we are going to use. If you want to be convinced, put some numbers here. Put an angle of a positive particle with respect to this plane. Let's say the plane is at 0 angle. Put the positive particle at pi by 2 roughly, and the negative particle is at minus pi by 2, and then you get a number 1 for a opposite sign when they are opposite sign. And now you put same particles, plus plus, both of them will be pi by 2 or minus pi by 2, doesn't matter. You will get a different number, minus 1. So now you see this observable can tell you if there is really a charge separation along across the elliptic flow plane, which means along the magnetic field. This is the most difficult slide in my talk, and I wanted to say that. So remember now, I will not present individual gamma for opposite sign and same sign, all the time. What we are interested in the difference between opposite sign and the same sign, means a plus minus compared to either a plus plus or minus minus. So this, the delta gamma observable is the primary CME observable, has to be greater than 0 if there is something interesting. Okay, but there is a problem that you need to first note that is there any other process that can mimic this signal? And there is actually one mechanism that was realized to exactly mimic non-CME phenomenon that exactly mimics. Imagine a situation where a neutral particle is produced in the event. It has no charge, like a rho meson or something. Now, which way is that neutral particle emit, right? It can emit in any direction, but remember I told you this axis of elliptic anisotropy is what it represents is that it represents a more probability of any particle, like roughly 8% more. So there is a 8% more chance that this neutral particle will emit along this axis. Now what it does, as soon as it tries to emit, like it has to either go right or left, what it will do is it will force a pair of opposite sign particle go together in one direction, either right or left. Okay, you see it enhances the opposite pair correlation along parallel to that plane, and now you put the number for a positive and negative. It will be 0 0 0. You have 1 here, Now, most likely combinatorics will tell you the probability of finding two positive particles is that if one is at 0, other will be at pi. So now you have again, this will give you -1. Now you have a situation that is indistinguishable from what I said before, which is the scenario of chiral magnetic effect. So the delta gamma now, which is a fake signal, the same observable experiment, you will not be able to tell. So delta gamma is again the difference between opposite and same sign, is now related to a non-zero number, which is related to how elliptic this event is, means what is the probability of this rho meson to go along this psi 2, which is basically the V2 of rho meson, and there is a 1 over n. This 1 over n is interesting because if there was no elliptic anisotropy, this process would have been just a random walk, and it would have been just suppressed by the number of rows. So 1 over n is obvious, right? Because it's a random walk, and then this extra physics is coming from flow, right? So it's an effect of flow and charge conservation. That is a signal. Okay, I think I'm moving a little slow, so I'm going to have to speed up. Now I'm talking about the first measurement at RHIC. Okay, the first measurement at RHIC was done from this for this gamma observable. Here we are not showing the difference, but I will show you the I'm showing you the individual opposite sign and same sign. So this is the observable represented as a function of centrality. There is 0. Note that. That's the first thing you should note. And then there are a bunch of curves. Blue open. This is from copper-copper collision, which is a relatively small system. Excuse me. And then there is another system, gold-gold, solid, blue. But the points that are close or above 0 are for opposite sign. So we are now looking at if one of the alpha, phi angle is for positive particle, the other one is for negative. So they are above 0 here. And then the solid circle is again for gold-gold, but it is for same sign. We are looking at if one particle is negative, the other has to be negative. That's for gold-gold. And then this open red is for copper-copper. So first of all, what you see is that there is a difference, clear, significant difference between opposite sign and same sign. So delta gamma, this is the gamma, okay. So there it's non-zero, right? So that's the first observation, which means that this indicates that there could be, so this observation is consistent, this observation of charge separation is consistent with exactly what you would expect for CME. But because we cannot distinguish, you also have to associate the process of background, which is due to this resonance that I told you. And we don't know which one is causing it. But notice one thing is that the small system, the difference between this blue and the red, the opposite sign and the same sign, is larger than the larger system. Why there is more charge separation in the small system? That was puzzling. Is it because the magnetic field is larger in this copper-copper? That is not true. Magnetic field is not large in copper-copper than gold-gold. So this is not consistent with what you will expect for CME. So what is it? It was realized that this is due to purely conservation effect due to digests. There is a name for effects that are due to conservation. We call them non-flow. There are a couple of other sources of non-flow also, but dominantly long-range effect due to conservation. Correlations generated from conservation, long-range correlation generated from conservation is called non-flow. That causes it. Why it is larger in copper-copper than gold-gold? Because the digests are not tamed. Digests are not tamed in smaller size system compared to larger size system. Larger system, they quench these objects, and the effect is smaller in larger system. So mathematically, if you want, I want to say what I am going to measure now. I have an observable delta gamma. I want to measure this in experiment. I know that there is a excuse me. I know that there is a contribution from signal. Let's call it delta gamma CME. We don't know what fraction, what is the fraction for this component. We'll figure that out. But we definitely know there is a background which is related to V2 and isotropy over multiplicity. This is just the resonance I told you. And then now there is a second background called non-flow. So let's know a little bit about this mysterious last component, which can be known by, which was very well understood from this LHC experiment, which took it to a little bit extreme. Note that previously we did gold and copper. Gold was large system, copper was small system. LHC they did lead and proton lead. Okay, proton lead is a much smaller system because the proton is this. And note one more thing, that if you think of a heavy ion as two current carrying wires, you have to think of a proton lead as like a wire that has, it's basically a wire, but there is a wire inside it. So if you have a situation like this, if you go to Griffiths or something, the magnetic field inside this second wire, which is random, which is in P-gold system, the direction of the magnetic field will be random. Because it is random, you expect no signal in this proton lead system compared to lead. But in lead you should have AA, you should have signal. But what was noticed was interesting. This is again the gamma observable written in a slightly different way as a function of multiplicity. Solid blue points are that are above 0 are from P lead, and then open blue are from lead. You see that lead goes to higher multiplicity here. And then the same is, kind of convention here. This is opposite sign, this is same sign. Of course, you see difference between opposite sign and same sign, but the interesting thing is that the lead has the same signal as P lead. Okay, so what do we have here? Now in AA system, again, back to my equation, I have a signal, I have a background 1, background 2. Now we know this left hand side, the measurement is same is in PA, but we know that there will be no signal in this small system, but we know there will be background 1, background 2. So this left hand side is same. So what do we are after is that, can we prove from this that this term, CME term in AA is 0 or non-zero or something? You can immediately see that you cannot do that because you have two equations. You have 1, 2, 3, 4, 5 unknowns. And the reason why they are unknowns is because this term is different in lead than P lead. This term is different in lead in P lead. So from two equations and like 5 unknowns, you cannot do anything, prove anything that whether CME exists in heavy ion or not. That's our goal. We want to prove that this term is non-zero here. So immediately it tells you something, that what you should do is that you should try to have better control of this term. If it would have been very good if these two terms are same, these two terms are same. Now of course, because they are same, you could have immediately proven that this is 0. But we know that they are not they are not same. So this immediately gives an idea of you should do this measurement in two systems that are of similar sizes. Okay. So what are the possible candidates? Systems that are of similar sizes. You have to really search into this chart of nuclei in the Z versus N plot. If you look at the periodic, this is not a periodic table, this is just a chart. And there are several candidates. So one candidate over here are, what we are looking for are isobars, is ruthenium 4496, and then this is the zirconium 4096. But that's not the only choice here. You have a bunch of other choices, like for example, if I am right, this is selenium 136, xenon 136 is another candidate. But this was chosen by the accelerator and based on the availability and the lifetime. So this is the one that we are going to use to collide isobar. But remember one thing, that the isobars, you have to have a difference in the proton number, so that your ultimate goal is, of course, you want to have same size, but you want to see the magnetic field is different between the two. So here comes the isobar collisions. We are going to collide zirconium on zirconium at RHIC at 200 GeV, compare it with ruthenium at the same energy. Remember, the ruthenium has 4 extra proton, so the magnetic field will be slightly larger. Magnetic field square is important for our observable, because I told you, if you remember, we are measuring a pair, a triplet correlation, and what happens is we are measuring actually a quantity that is more close to like current square, not current, and in CME current is proportional to B, so the measurement is most related to what is important is B field square, and that is 10 to 18% larger in this system. Now we have a nice situation here. In ruthenium, you will have signal, you have background 1, you have background 2, which is due to non-flow. In zirconium, you will have again the same thing. But the most important thing is that because these systems are of same size, size means the total number of nucleons are same. So non-flow, we expect quenching of jets and other whatever conservation effects are going to be same, that are charge blind. Conservation and well, I shouldn't. In simple way, it's basically just because the sizes are same. These terms are going to be very close, and then you have to now see how close these two terms are, and we know that they are going to be different, but we have to see how these two terms are different. So basically, it's much better control than any previous experiment. Okay, so I removed the last two terms. So I have now ruthenium, zirconium, I have the CME terms and the V2 terms here, the V2 over N or terms. Now when we were actually designing this, how to do the experiment, proposing it, that time we thought the multiplicity, you see this N here, we assume that this N is going to be same, and then this constant K, kappa, this is a fundamental constant related to conservation or something, freeze out or local charge conservation. So these we assume to be same. So but V2 are different and these terms are different. So then you have an equation. Let's get this V2 on this side. So you have delta gamma over V2 in ruthenium over delta gamma over V2 in zirconium will be 1 plus a fraction of CME in zirconium related to times not related to times the ratio of the magnetic field square in ruthenium over zirconium minus 1. So because this is 18% larger in ruthenium, so this term minus 1 is 0.18, and this one, which is FCME. FCME means if you take ratio of CME over the total, that's the term. This is unknown, we don't know what it is, but one thing is sure, because it's 0.18, this is a number. If this term is non-zero, so this whole ratio will be greater than 0. So that's the condition for CME. But we don't know what this unknown is. If this FCME is 0, then this two ratio is going to be 1. So we have a very well-defined experiment now. But we need to now know that how much significance we do. Like we need to be very specific about the experiment. Because we don't know what is FCME, we want to know how much would be the signal given a FCME. We are plotting here 1 minus FCME, which is the background. So basically here is a number. If we have 20% signal, which means FCME is actually 0.2. So 1 minus FCME is 0.8, 18% background. If we have collisions of ruthenium and zirconium, each of the collisions we get 1.2 billion events, then we will be able to measure, this ratio with 5 sigma significance. This is the proposal, experimental proposal, but it immediately tells you something that the background is of the order of this small, the signal is so small that a precision of 0.5% is needed, which I don't think, we ever attempted in this kind of measurements at RHIC. This is like this is gonna we have to push our limit. This is based on statistics, and the main problem is that even if you have a statistical precision, if you want to achieve a statistical precision of 0.5% based on the number of events, you have systematics that is could always be large and kill the nice experiment. To reduce systematics, what we did is at RHIC we collided zirconium for like 20 hours, and then we switched to ruthenium. Then again we switched to zirconium, and we go in back and forth between the fields. And the reason why we did it is that the detectors, the conditions or the run conditions will affect both the species in the same way. And what will happen is that we will, at the end of the day, when we take ratio, we will be able to cancel the systematics. So we took a lot more data, and then we switched to what is called the blind analysis. Why do we need to do blind analysis? Blind analysis is needed to remove biases. Okay, and this whole procedure is a very complicated procedure. It is done in 4 steps. So first step is basically a mock of all the other steps. So it took 2 months to test all the other steps. So from step 2 is actually the step, the real analysis. So first step, it took 1 year. What you do is you provide the analyzers not with ruthenium and zirconium data. So remember, we know that the signal in ruthenium will be larger than zirconium. We know this before we begin, right? So if we know this, then there is a lot of chance to introduce biases. So first step, what you do is you don't provide the analyzer with the data, you provide a mixture of ruthenium and zirconium, and ask the analyzers to develop all the codes and freeze the code so that you don't touch it. Okay, you not only have to develop the analysis code, you develop all the quality assurance code as well. So this is what is called established procedure. It took already like 1 year, and after that you can act completely blindly. Okay, so means someone else can take all the code and do the analysis. So actual step 3, which took like half a year, is called blind analysis. So in this step, you give more data. This time you separate ruthenium and zirconium, but don't give enough data where so first of all, you don't tell analyzer which one is ruthenium, which one is zirconium. And you also do not give enough data so that they can get anything statistically significant. The purpose of this step is actually where you actually use this previously created code and do quality assurance of the data. So reject some run or data that is bad. Okay, so that should be done. Once that information is there, you go to the final step where you actually separate ruthenium, zirconium, and do the full analysis and directly publish the material. But there are certain norms of blind analysis. What you have to do is you have to write every details of what you have to do in a document, and if you don't write it, you cannot do that. Not only that, you have to also write what will be the case for CME for the observable you want to study, and what will be the interpretation of the observation. You have to write it down, you have to predefine it, and you cannot deviate from this. Okay. And all the method is, if you want to know more, all the method is, can be found in this paper. There is one more thing actually, that while removing bad data, like cleaning up, we do, experiment, we do a lot of cleaning up. Someone can introduce bias. Someone can just remove more zirconium data in such a way that the ruthenium sample looks bigger. So there will always be bias. That's one thing. Whatever is the actual thing, you end up doing something else, you bias. There is another thing is called noise. Noise means the same judgment when you use your best judgment. There is you introduce a variability because due to heuristics. So no heuristics is allowed, no bias is allowed in a blind analysis. You completely do clean up and QA using algorithms. So some of these ideas are very common in behavioral economics or somewhere that we borrowed. So there were 5 independent groups that will do the analysis. So group 1, 2, group 1, 2, 3, 4, 5. Now the idea is that, let's say group 1, which is this UCLA group, they prepares their code, software analysis tools. That analysis code will be run by, let's say, Stony Brook and UIC group. Their analysis will be run by another group, which is, let's say, Wayne State, Tsukuba. And again, their analysis code will be run by a different group, which is, let's say, BNL Fudan. And then their will be run by another one. Okay, like that, or or the other way around. So, the final group is Purdue. So no one is 5 independent group will perform the analysis. No one can run his or her own code. Another person will run. Only thing the analyzers who develop the analysis tool, they will do is they will open the box, and whatever result you get directly, you present it. I think I'm running out of time. So here is one example, like for BNL Fudan group, they were here, and then ruthenium was run by one of the star member who was in Russia. And the zirconium was run by one of our member who was in Japan, and then once they send the result, we just open the box and present it. It's actually interesting that, remember, ruthenium, why I did send the ruthenium to Russian colleague. Remember, ruthenium was discovered by a Russian, and the zirconium was not discovered in Japan, but the technology for zirconium came from Japan. So it's a weird connection. The last few minutes, let me quickly go through results. First shock that we have, actually interesting thing is that I'm plotting multiplicity, average multiplicity in ruthenium and zirconium shown by solid and open as a function of centrality of collisions. And here is the ratio of ruthenium over zirconium, and you see that the ratio is above 1, and that's the first thing it was unexpected. Remember when I told you before, when we were having this designing this experiment, we thought that the multiplicities will be same, but we saw that multiplicity is larger in ruthenium than zirconium. It is probably because one of the explanation is that the zirconium is a slightly smaller size. Possibilities the ruthenium is a slightly smaller size nuclei. That's the first result. Multiplicities are different between these. Then the results of elliptic flow. So elliptic flow is measured according to these equations. I told you cosine phi.
Sorry, go back to the previous slide. I wanted to see which one. So the higher multiplicity comes from the larger nucleus, right?
No, smaller, because the energy is same. The density is larger in the ruthenium.
Thanks.
So now let's talk about the elliptic flow results. I'm sorry, Rishi, I'm running a little low on time, but I hope you have give me a few extra minutes. So we are going to measure elliptic flow, which is a measure of using 2 particle correlation. So this is our detector TPC. So you take the first particle at some value angle, and then for the second particle or the plane, you start to introduce gap. So you could take it very close, you take it from the other side of the half of the detector, or use other detectors. So as you increase the size, follow the color here. This is what I plot, elliptic anisotropy V2 as a function of centrality. Upper panel is zirconium and ruthenium. Always in my plot, zirconium will be open symbol and ruthenium will be solid symbol. But you notice that zirconium and ruthenium, here it's difficult to see the difference. But yellow to blue to purple to green to red, it's basically changing the gap in rapidity. As you increase the gap in rapidity between the 2 particles, it goes down. In peripheral event, the difference is stronger. As towards central event, they are more or less consistent. So different methods, right? Now look at the ratio of ruthenium over zirconium. First of all, it is above 1. Okay, with good significance in all different methods. Then it goes to 0 towards central event, and then it goes up again in the most central event, which is very interesting, right? In this central event, the nuclei are overlapping on top of each other. There's like no impact parameter. So if you see a significance here, it means that one of the possible things is that the ruthenium is actually a more prolate more deformed than the zirconium. That's one of the possibility. Okay, so that was unexpected. Okay, which is also very interesting. Let me move on to CME observable. You already know the definition, so this I hope would be quick. First thing is this charge separation by elliptic flow. I already told you this observable, but remember we now have to deal with 3 particles. So first particle is in our TPC. Let's say it is a positive charge particle. Then you have a negative one also from TPC, but you have a choice to choose the third particle, which is the event plane, and there again you introduce gap. So I'm going to not have all the arrows for all the results. I'm going to show 2 actually. One where the plane is taken very close or from everywhere, and another it taken from this green, which is the other half of the TPC. So note that what we are looking for is this ratio I told you before, delta gamma, the difference in charge separation opposite minus m over V2 in ruthenium over zirconium ratio. We know that if there is CME, it has to be greater than 1. Look at the data, ratio of delta gamma over V2, 2 panels as a function of centrality. 2 panels is the top panel. I told you there is the gap between the particles and the plane is not there here. And in the lower panel, there is a gap between the particles, charge carrying particle and the plane. So that's the difference, upper and lower. But there are different color points. They came from these different groups. I told you group 1 uses event plane, group 2 uses 3 particle correlation. It doesn't matter, right? They are consistent. So here is, here are the data points. First thing you notice is that here you have 1 and all the data points are below 1. Okay, except here everything is consistent with 1. The same is also true here, except for maybe over here, everything is below 1 also, right? So the predefined criteria that we had, that ruthenium, delta gamma over V2 has to be larger than zirconium, is not seen. So we do not see this signature that we have. This is not the end of the story. There's a lot more. Let's do something else now. Let's use an experimental baseline. So this is what we are going to do. Let me tell you what this is. So this is our conventional measurement. We are measuring charge particle, charge separation across the event plane. Why we are measuring this? Because we want to measure charge separation correlated to the magnetic field, right? And that's how you get this condition, right? Delta gamma over V2 ratio in ruthenium over zirconium has to be greater than 1. Let's remove this correlation with respect to event plane, or which means let's remove this correlation with respect to magnetic field. Now let's just consider just the charge separation. Let's take a pair of opposite charge and same sign charge and build a correlator that has no event plane. That's this definition, just the phi 1 and phi 2, like phi alpha, phi beta. This could be positive, okay, opposite sign, sorry, positive, negative, or negative, positive, which is opposite sign, and then the positive, negative. You see, there is no event plane. So this, if you see a non-zero value for this quantity, it is not going to be, it may or may not be related to CME. It has no correlation, right? It's more random. But so what will happen now? We had this old criteria. Now we are going to do a revised criteria. It's very obvious here, right? So the one for which you have a correlated charge separation with respect to magnetic field, that ratio for ruthenium over zirconium has to be larger than the ratio of this uncorrelated charge separation in ruthenium and zirconium. I call it delta. Notation doesn't matter, right? But I hope you understood it. Why? What is the reasoning behind it? So this will be our new predefinition, and we are going to test it in this slide. So this is, again, I rewrite it, but we do a little bit of, make it compact. Let's get this delta on this side. This guy will go up. Define in, a compact quantity, delta gamma over V2 by over delta. So you have just one number. And then this equation means that kappa, which is this new thing, ratio has to be greater than 1, and that was measured here. Kappa solid is solid circle is ruthenium, open circle is zirconium, plotted as a function of centrality. That's the upper panel. Lower panel is ratio, follow 1. Here also you see this ratio is below 1, right? So this predefinition that we had with a good significance, we see that is also not observed in ruthenium over zirconium. So predefined criteria for CME in this observable is also not seen. Let's do another thing, okay? Very much along the same logic that I had. This is our conventional measurement, charge separation across magnetic field. And the magnetic field, why do we know it is correlated to magnetic field? Because we are measuring elliptic anisotropy. We know they are correlated. But there is another flow, which is called triangular flow, which is related to a triangle. And the anisotropy direction, which is corresponding plane, psi 3, is random. And we know that this is going to be uncorrelated to magnetic field, completely random direction. So, you know, so this was the primary observable, charge separation with respect to second order plane. Now we are going to define a slightly different one, charge separation with respect to third order plane. And I don't have to tell you what will be the new criteria. It's very simple. The delta gamma over V2 in ruthenium over zirconium, this time it has to be greater than the delta gamma 1 to 3 over V3. Basically, charge separation over third order plane, which cannot have any contribution to CME because it has no correlation with magnetic field. At least this ratio has to be greater than this our other ratio, okay, the original primary correlator. Why are we doing all of this? Because we know that, who knows, maybe this ratio greater than 1 is probably not the best baseline. So these are more experimental driven baseline. So here is the result. Again, I have a conventional correlation of magnetic field with respect to psi 2. This is a signal plus background, both has, but this other one, third order, has 100% background. So psi 2 correlation, the primary one is shown here on the upper panel. This is delta gamma over V2. Forget the N part. Actually forget the two upper panels. So top panel is over with respect to psi 2 plane. This middle panel is with respect to psi 3 plane. But look at this plot here, the ratio. The black is I am showing only 20 to 50% centrality. So the black is the result for charge separation with respect to second order plane. Second order plane is correlated to magnetic field. This is the average gray band. The blue is with respect to third order plane. Blue has larger uncertainties because third order plane has less resolution. It has a wider band. But what you don't see is this black and blue are, according to this predefinition criteria, the black should have been significantly above blue, which we don't see. There is also a red. Red is just the ratio of delta delta that I told you before. It's basically, I already showed you, the black is below red. Black is consistent with blue. So this predefinition CME criteria is not seen. But you notice something interesting, that everything is below 1. So things are not 1. Of course, things are not above 1, which would have been really good if the black was above 1. But even these background measures are everything is below 1, which needs some explanation, and I will get to that in last slide. We studied also, I'm hitting 1 hour limit, so I have a couple of slides. We studied one thing also, that we want to know. We know that the correlations that develop very early in the system spread in wider range in rapidity. So we studied this same observable gamma as a function of the rapidity gap between the charge carrying particle, and tried to see whether there is a rapidity dependence. I don't want to go into details, I can come back. But the point is that we see rapidity dependence, but we don't see anything that is different between ruthenium and zirconium. We did study it with centrality, 2 different detector. This difference between the left panel and the right panel is varying the gap. Well, that's the point, right? No difference between ruthenium and zirconium anywhere. So all the points, blue is zirconium, red is ruthenium, they are on top of each other everywhere. Another thing also we did, we know that the background is causing by resonance like Ru+Ru. So how about plotting the signal as a function of invariant mass? So we know that resonance show up as peak. So if there is a background driven thing, it will show also peak where there you expect a resonance, right? And question is that if the resonances are, produced resonances are same in ruthenium and zirconium. So if you take the difference between ruthenium and zirconium, whatever will remain may be related to CME signal and its invariant mass dependence. Invariant mass is interesting thing in this context. But anyway, what we saw is after we took difference, the difference is like consistent with 0 in our measurement. Okay, in the blind analysis, you cannot do anything after you have opened the box. Okay, but there is a small section allowed in the analysis which you have to refer to as post blinding, but it has to be very limited. And there we try to actually address this thing that I told you before. So remember, our criteria was delta gamma between ruthenium over zirconium has to be greater than 1. And this came from these two equations that I told you. Remember, I assume n in here are same, but that may not be true because, well, may not be true. We saw they are not true, but we didn't know it when we started the blind analysis. So a better criteria would be not delta gamma over V2 in ruthenium over zirconium, but 1 over n, a better criteria would be that this ratio is not greater than 1, but this ratio is greater than 1 over multiplicity in ruthenium and zirconium. Okay, because there is 1 over n here. So this should be compared, and that's what I am showing here in this ratio. This is already ratio of quantities in ruthenium and zirconium in 20 to 50%, and these are different points from different groups and different methods. And here is the last point here is 1 over multiplicity, this quantity, in actually ruthenium over zirconium, this point. So this is this number, and this left term is these various different points from different groups and different detectors. So if this is the line, which is our new baseline, you see that the points are close. Sometimes they are above with some significance, and depending on what method you use, they are sometimes consistent with each other. So you see everything is below 1 now, but because of the multiplicity difference, what is possible that the new baseline will be shifted here. So you have to probably compare with this purple band. But this is over. I just wanted to one slide and I end my talk. This is in 20 to 50% centrality. You could do something else. This I took from Sergei's talk, which was given a few days ago. This is the plot I showed you before of multiplicity in ruthenium over zirconium as a function of centrality. Ruthenium, I told you as a response to Sorendu's question that ruthenium has higher multiplicity than zirconium. So what you do is, this is ruthenium over zirconium, you flip it 1 over n charge in ruthenium. This is what you want to know, and this is what you wanted to compare to this measurement, these other points, which is charge separation, and this is our new baseline. You could see that they kind of follow this multiplicity. Here you see a little bit of difference when there is no gap between particles and the plane. Here the gap is introduced and the difference kind of has disappeared. So this may be a better baseline, and now we have to understand that is this difference between this baseline and these points, whether you can accommodate a signal there, if you consider the if you could understand that why they're different in the top panel and lower panel with rapidity. So that's the conclusion of my talk. I don't want to read it, but let me tell you one thing, that our original plan was to get a precision of like 0.5% when we designed, ask for the collision. We actually achieved 0.4% precision. That can be seen from this plot that I showed you. this is 1 and this is 0.98, 0.96. So you see the precision of our data is actually very remarkably good, and this is 0.4%, the smallest one that we have. So that we have achieved from the experiment, but we do not see any CME kind of we do not see anything that is consistent with predefined criteria of CME. But we did a post-spline analysis, and if we consider the effect of multiplicity difference, the thing we need to see is that in future whether we can accommodate a small fraction of CME signal. But I have to say that this whole program was a success. We had a lot of confusion over this topic. We have narrowed it down significantly, and now the future program will probably try to look for an upper limit at 1% level. Thank you, Rishi. It took 10 more minutes. Thanks.
So, are there any questions?
Yeah, I have one small question. First of all, it's an interesting result because, although negative, I had a question about that multiplicity plot again. One of your last slides, right? That one. Yeah, right. There's that little kink there, and I was wondering whether this is one of the shells is filled and the other is not. One of the either the proton or the neutron, one of them is filled and the other is not. Is that right? Closed shell, one non-closed shell.
Oh, you mean the nuclear structure? You are saying that this could be related to the nuclear structure of the isobar? Yeah, actually, what you should look at is not just the mean multiplicity. What you should look at is what you should be looking at is the distribution of multiplicity. If you really want to think in that direction, I would refer you to look at the probability distribution of multiplicity and look at this shape, the ratio of the probability distribution, and it has also this weird shape, and we are trying to understand why this is this related to the cell structure, and there is a density functional theory calculation, which is what I'm plotting here in the red. That kind of gives an explanation, but the thinking along the line of what you said is probably a good way. So this is a much more fundamental quantity to look at, the probability distribution of multiplicity. When you average, there are a couple of other artifacts come. Average, remember that when you average over a wide beam of centrality, there are also some experimental artifacts that come in the averaging. You know this from probably you might have heard from other analysis as well. And how you define the centrality, how you treat integers, float, or so this is how wide it is, right? How wide the centrality beam is. So depending on that, this difference, this 1 or 2% difference, could have several sources, including the physics that you also mentioned. So we have to understand.
Thanks.
Other questions? Okay, so
Rishi, I have a question.
Go ahead, Raj.
Yeah, Prithwish, the standard way to eliminate non-flow effect is to introduce large gaps, rapidity gaps.
Right.
Doesn't work here, does it?
For 3-particle correlation, or
yeah, in general, for any correlation, you introduce rapidity gaps, so that it's unlikely or less likely that they're coming from resonance decays or any other non-flow effect.
Yeah, for 2-particle correlation, you kill it immediately, because this is just 2-particle, and the resonance decay. So one of the positive and negative will be just these 2 angles. So you immediately kill it. And for 3-particle, before I tell you this, So you kill the short range correlations due to resonance, but the long range will be there, which is due to momentum conservation.
That's right.
So you cannot remove it, and the long range is, you could see it actually, that long range has a 1 over n depend. So everything has 1 over n because they are random walk. So you know, so this reduction is mostly due to short range reduction, short range on flow reduction, and the flow fluctuations, and also even plane decorrelation in this. Now, when you come to 3 particle correlation, it is also a series of the broader how do I say, the family of these objects. 3 particle correlator is something like what you introduced a long time ago with Jean-Yves. You can see that there are 3 particles, right? And it's tricky where you want to use the gap. So what I am doing in these plots is that there is no gap between the alpha and the beta, but there is a gap between alpha, beta, and the plane. So you reduce some non-flow between the these 2 particle and this. So the plane is far. But remember, a resonance resonance will decay to a positive and a negative. So a resonance will decay to phi alpha and phi beta, and that doesn't take care of the fact that the resonance is the charge, the pair that is being decayed has its own correlation. So with this you increase the gap between the resonance rapidity and the plane, but you are not introducing any gap between the 2 decay daughters of the resonance. So that you can't, right? So they will be there. It's complicated because it's a 3 particle, right? So you can always immediately, but anyway, let's not go there. But this gap between the alpha, beta, and psi 2 also helps to reduce the other non-flow, because if you have all of them at the same, all 3 particles at the same rapidity, you will have much larger non-flow. So indeed, you see that indeed it is true that when you have the sub-event, which means alpha, beta are from 1/2 of TPC, and the green is the plane is from other half, you really we know that this has less non-flow. This is a more, that's why when I had the last slide, the fact that in this case the multiplicity is consistent with 1 over multiplicity is consistent with the charge separation, we are much more confident of this in a sense that we know the non-flow is more controlled here. I don't know if that answers part of your question.
Okay.
Oh, actually, Rajiv, there's also a study with the rapidity gap between the charge particles. So this may be of your interest with for the resonance. Maybe take a look at this later.
Thanks.
Okay. Prithwish, I had a naive question. So it's I think maybe 41, slide 41.
This
No.
one?
No. So I think, so maybe just go back 35, around 35 then. And this should work, yeah. No,
this one?
Yeah. So in all the plots, I mean, it's clearer in the final results, but you had this most peripheral bins which are significantly lower.
This one?
Yeah, or in the bottom plot in particular. So you had a flat region in the centralities of around 60 to 20, and then at the very peripheral region you had a drop. So you fitted the flat region. Is the idea that the magnetic field is largest in that region for those centralities? So what is odd about this last centrality bin?
The which last?
This one.
Peripheral or the central?
No.
This. Yeah. So first of all, the magnetic field is not large. So it's probably common misconception when people say magnetic field keeps increasing as you go peripheral. It's
I
not
understood.
actually.
Yeah, I
It's
understood.
not actually. The reason is the decorrelation, the angle of the direction of magnetic field is very random here, with rest compared to the participant or the plane. So magnetic field is not really large here. So they are in fact small, and that's not the reason, definitely. And even if it was large or whatever, it still doesn't explain why it is more below 1. And I think one of the reason why, first of all, you see that this has large uncertainties in this beam, and maybe I should go to the this plot, and that has probably an explanation. You saw that the multiplicity also went down here, right? Just the multiplicity ratio, and I think this is more like a multiplicity scaling. So what you have in these events is like very small multiplicity. So what you are just seeing, charge separation here is mostly dominated by mostly like a random walk. It's just 1/n, mostly like random walk due to all those conservation that I mentioned before and non-flow. That's one of the reason why it drops. So there is one more thing I must tell you. You see that error bars are much larger in these points. So if you are interested, I could tell you another thing. The experimental efficiency to trigger these events are much lower. So what we have in this region is we have to do a large correction because of our trigger inefficiency, and that kind of causes these large uncertainties. At this point, like, could be anywhere from here to like, you could see, you understood the point, I guess.
Yes, I got it. Okay, so are there further questions? I'll stop the recording now.
I have one question, Rishi.
Okay.
So Prithwish,
yes.
So it looks like from this plot, so finally, probably it is boiling down to the fact that the multiplicities are not similar, and some uncertainties or our ignorance about the global modeling of that thing. So then is it possible to analyze, say, same multiplicity event of ruthenium and zirconium and compare them?
Yes. First of all, thank you, Sandeep, for bringing this point. You can, right? So we just didn't do it because we decided to do it. So what you are saying is that this is the probability distribution of multiplicity in ruthenium and zirconium. So we decided to do the analysis in centralities, common centralities. But we could have chosen to do it in same multiplicity bin. We could have, but the strict rule of blind analysis we followed, and we didn't do the other one. But you are right that we could do it in multiplicity bin. But remember one thing: even if you do in same multiplicity bin, if you take very wide bin, then what happens is the shape of the multiplicity distributions are different. So we are talking about 1 or 2% difference here, right? It's a very tiny signal. So, oops, there I have the mess. Let me go back to the plot here. So we are talking about like 4%, right? 1 or 2% difference. I'm so sorry. So you are interested in to understand these, right? Why these points are above multiplicity, right? So this is just like a sub%, right? So 1 or 2% difference. So even if you do, let's say, you want to do the analysis in same bin, because the shape of the multiplicity distributions are different, you can look at in the ratio. The mean multiplicity will again be different, even if you take the same bin in multiplicity, just because the probability distribution has a different shape. So what you have to do is, you have to take narrow bin, And if you take narrow bin in multiplicity, you run into other problems, like same problem as I think all of you are familiar with moment analysis, and doing things in one bin in very narrow bin in multiplicity is not a very always viable thing. You introduce large statistical fluctuations. So we can, but we are thinking of whether what to do.
Okay, and possibly if you do same multiplicity, then do you also fear that their shape could be very different?
Oh, you see already the shape. You see already the shape is different.
For centrality. Okay.
Say again.
I mean, that's why did you opt for centrality? Is same centrality to have the?
No. That's not why. We didn't know the so before we started the analysis, all the models kind of predicted that the multiplicity will be same and between two isobar in 20 to 60% centrality. So 60% is difficult, so we did all the analysis in 20 to 50%, right? Because all the models were showing before the bind analysis, multiplicity will be same, V2 will be close, and the signal will be different, right? So this is why we did, but we could have done. But Sandeep, note that this plot is a ratio of the multiplicity distribution, this gray. So you see ruthenium over zirconium, it goes down below 1. It goes up again to 1, and then it shoots up again. And then this is what Zorindu was referring to, that whether it's a nuclear structure or some explanation there. Yes, probably. So if you want to really do the analysis, you have to choose where this is 1, right? Somewhere here, 150 to 200, and give it a try.
Okay. And just one small information. So what is the rapidity coverage right now with this experiment?
So there are a bunch of experiments done, right? So first points that let me just, you could look at this plot.
No,
so
I mean, not for the analysis, but I mean this ruthenium zirconium data when it was taken, what is the available rapidity coverage maximum range?
So for charge particle measurement at mid rapidity it was ±1, and for even plane you have a bunch of options. So first 3 points are with everything in TPC ±1, all 3 particles, and then second next 4 points where the charge carrying particles are from one half and the other half. And then I didn't get time to show you. There is also even plane detector, which we use to measure the. Where do I have that plot? I don't have it. It seems. We also had the even plane detector, which is 0.2. So 2 point, which is 2.1 to 5.1. So whole TPC you can use the charge particle. So to measure the charge tracks, and then the even plane you could take outside.
Okay. Thank you.
Okay. Okay, so I will, I guess, stop sharing. Or maybe, can you hear me? Or I lost the microphone or what?
No, we can hear you.
Oh, I see. But I think we cannot hear Rishi.
Maybe.
All there.
Rishi
is muted
right now.
Oh, I see. He muted, I guess. Yeah, so Sandeep, also the beam
Yeah.
energy scan 2 data are being analyzed. So it will come very soon. I don't have
Okay.
time to go there with these EPD detectors and then also run 2023.
So EPD is also detecting charged particles, right? Or is it-
Depends. So yes, it is also right. So it always detects charged particles.
right. But you are saying
But
it could be spectator and not produced particle. Is that what you are trying to say?
it can detect fragments. So spectator you can never detect in
Okay.
other than 0-degree calorimeters, because spectator means something that didn't participate, like it didn't even have anything. So the Fermi momentum is going to carry it through the beam. So it doesn't have you have to see, like statistically it will end up, but the stopped proton will be detected, and the protons proton determine the magnetic field. So it gives you a handle on the magnetic field much better at low energy. Remember, low energy, right? Not high energy.
Right. Yeah. Okay.
Okay, so
Thanks, Prithwish.
I have to. It's 9, so I'm gonna have to join something else, and I don't
Okay.
hear from
Yeah.
Rishi, I guess.
Yeah, maybe some technical.
He's me. Oh, I see.
I think he's busy in a call. So are there any other questions? Otherwise, maybe we can. Okay, I think there are no other questions. Thank you, Prithwish.
Yeah, thank you so much,
Yeah.
Bhaber. And you wish we, will be able to visit at some point to India, and maybe
Sure.
if I visit Mumbai, definitely I'll come by.
Yeah.
Thank you all.
Thank you.
Thanks.
Thank you. Thank you, Prithwish. Bye bye.